All right, here we go for the problems for chapter 24. It says a supernova that has a luminosity of 10 billion times, all right, which is of course 10 to the ninth, times the luminosity of the sun, is used as a standard candle. Okay, so this is the method of standard candles that we're about to use to measure the distance to a faraway galaxy. From Earth, the supernova appears as bright as the sun would appear from a distance of 10 kiloparsecs. What is the distance to this galaxy? So, 10 kiloparsecs is, that would still be within our galaxy. So what would a star that had the exact same absolute magnitude as the sun, what would its apparent magnitude look like from 10 kiloparsecs? That's what we're going to concentrate on first. All right, so these are the problems that we're going to do from chapter 24. I'm just covering the ones that are assigned for homework, and these are just sample problems. All right, so number 1, number 2, 3, 5, 6, and 8. All right, so one thing to note, you can't, I don't know this, I didn't write this very well. The absolute magnitude of the sun. Okay, so that's supposed to say sun right there. The absolute magnitude, which is capital M sub V for our sun, is positive. This is the number that we're going to use for this chapter, positive 4.83. Okay, so that'll get us better results. In the last chapter, I think I got a little sloppy and I used 5. I rounded this to 5. This will be a little bit better. Anyhow, all right. So here's problem number 1. This is what it starts with. It tells us that there's a supernova that has a luminosity of 10 billion times the luminosity of the sun. All right, and sorry, not 10 billion. 1 billion times the luminosity of the sun, and so that would be 10 to the 9th times the luminosity of the sun. And so this is the general equation that we're going to use. D equals 10 to the absolute magnitude minus the apparent magnitude, that's the little m, minus the absolute magnitude plus 5, and that whole thing divided by 5. And remember, D is always in parsecs. All right, so this problem requires 2 parts. First, we have to find the magnitude of the sun, the apparent magnitude, so little m, for the sun at a distance of 10 kiloparsecs. All right, so 10 kiloparsecs, of course, is just 10 to the 4th. So we're just using this equation up here, and we're going to solve for little m. Right? This is what we're looking for, little m. Of course, because we know the absolute magnitude of our star, the sun. All right, so 10 to the 4th parsecs is equal to 10 to the power of, in parentheses, the apparent magnitude minus the absolute magnitude, that's the minus 4.83, plus 5 divided by 5. So really, you just take the logarithm of both sides, multiply this 5, when you take the logarithm of 10 raised to any power, you get that power back. Of course, so we're taking the logarithm of both sides, so this becomes 5, right? Because this 5 right here goes over here, over to the other side. So it's 5 times the log of 10 to the 4th, and of course the log of 10 to the 4th is just whatever the exponent is, right? Because you're taking the log base 10 of 10 to the 4th. So this becomes 5 times 4, or of course 20. And so remember, you get everything, all of this stuff comes out of, comes out of the exponent when you take the logarithm, and so it's little m minus the absolute magnitude of the sun plus 5, and then you combine these two and then bring it over to the other side. So at 10 kiloparsecs, right? That's what this problem's about, or we're getting to that. At 10 kiloparsecs, the sun would have an apparent magnitude of positive 19.83. All right, so that's the first part of this particular problem. All right, so now that we know that that's what the sun would look like, remember that's what they told us in the problem. What, you know, if the supernova had that apparent magnitude, how far away would it be? All right, so we're about to remember the supernova has an absolute magnitude of 10 to the 9th times the luminosity of the sun. All right, so here we go. All right, so this actually takes 3 steps. All right, so the first step was to just figure out what the apparent magnitude of the sun would be, or our sun, at 10 kiloparsecs, and we found that that was positive 19.83. All right, so what we're going to do now is we have to figure out the absolute magnitude of this particular supernova. Now, how do we do that? All right, so we're going to use this equation. We know the luminosity of the supernova in terms of the sun, right? And so we know what this number is on the left-hand side of the equation, and that is, of course, equal to 10 to the power of the absolute magnitude of the sun minus the absolute magnitude of this supernova divided by 2.5. Okay, so now we can put the numbers in, right? So this is going to be, remember the supernova is 10 to the 9th, right? 1 billion times the luminosity of the sun, and of course, see if you. So here, let me just set it up first. It's going to equal 10 to the power of 4.83 minus m sub v. Remember, that's what we're really looking for, because then we're going to use that in the distance equation and then divide it by the whole thing divided by 2.5. All right, so again, what's the little trick that we always use when we have stuff like this? We just simply take the logarithm of both sides. So this becomes, remember, the 2.5 goes to the other side of the equation, so it becomes 2.5 times the log of the log of the luminosity of the supernova, which is 10 to the 9th. So in other words, the log of that is just 9, right? The log of 10 to the 9th is just 9, and so that's equal to. I put it up too far. That's equal to. So that's equal to. We've already brought the 2.5 over, so that's equal to what's left, right? And so what's left is 4. Remember, that's the absolute magnitude of our sun, and the reason that we're using that, of course, is because we know the luminosity of the supernova in terms of the luminosity of our sun. All right, and then minus the absolute magnitude of this particular supernova. All right, so then now it's just a matter of solving this. So it's going to be, let's see, did I multiply this? All right, so this becomes let's see, the absolute magnitude. This is just 2.5 times 9 minus 4.8, but then of course this is going to be this is a negative sign. Sorry, that's a negative, and so when you do this, it's actually pretty simple, and you just let your calculator do it. All right, so then m sub v. All right, so this is the absolute magnitude of this particular supernova that is 1 billion times the luminosity of the sun, would be negative 17.67. That's a decimal. All right, so that's how bright this supernova would be. Remember, the absolute magnitude always is talking about, what would its brightness be if it was, 10 parsecs away. You wouldn't want this thing to be 10 parsecs away. It would certainly be a lot brighter than the full moon. Anyhow, let's see. So the last thing that we have to do, remember, we've already figured out the the apparent magnitude, right? And that was up here, so it's positive 19.83, and now we've just figured out the absolute magnitude, which turns out to be negative 17.6. Okay, so again, this is a three-step process. This is ultimately what we're looking for is the distance. Okay, of course, you know, this is the equation we always use, is equal to 10 to the, remember, it's always little m minus the absolute, so little m, of course, is the, I should have said it in words, so it's always the apparent magnitude, which is little m, minus the absolute magnitude. See, that's why we had to figure out both of those numbers, plus 5, and then that whole thing divided by 5. And then, of course, the distance is always in parsecs, right? And so this is going to be a whole lot of parsecs. All right, so this, so if we put the numbers in, this would be 10 to the 19.3, positive 19, sorry, 19.83. All right, and then minus a negative, remember, so it's minus, but the minus the absolute magnitude, but since this is already negative, I keep doing that. This is already negative, so it becomes plus 17.67, and then of course plus 5. Right, oops. So that's supposed to be a 7. Plus 5, and then that whole thing divided by 5. Divided by 5. All right, so let me pause this for just a second. So this ultimately, everything in that exponent becomes 8.5. So the distance to this particular supernova is 10 to the 8.5 in parsecs. All right, so when you do this out in your calculator, it's a pretty big number. So it turns out to be 316.2. And then there's six places to the right of the decimal, and so that would be mega parsecs. So 316.2, if you will, mega parsecs. So that completes problem number 1. That's a very involved problem. Like I said, it took 3 different steps. All right, that's a little bit, the next ones probably won't be as bad. All right, let's look at number 2. Oh, okay, number 2 is actually pretty simple. I'm not even going to pause it. Number 2 is finding the distance to the Virgo cluster. All right, and so that they use, what do they use? They use a Cepheid variable. All right, so the Cepheid variable has, so this is the distance to the Virgo cluster. Virgo. So the cluster, not so it's not one particular galaxy. This is just the general distance to the Virgo cluster. So there's a whole bunch of galaxies. If there's a little spiral one and stuff. And so basically what they're looking at is, remember, the Virgo cluster has, well, a lot, what is it, like 1,500 something like that, 1,500 galaxies. So basically we're finding the distance to the middle of the Virgo cluster. All right, so they use a Cepheid variable, and they tell us the absolute magnitude of it is -5. I didn't read it. I didn't read it to you. Hold on. Let's. All right. So the Cepheid variable in the Virgo cluster, there's the absolute magnitude. There's the apparent magnitude, and then you just figure out the distance. It's pretty straightforward. All right. So they give us the absolute magnitude of this Cepheid variable is -5. Its apparent magnitude is positive 26.3. So then you just use this equation, or the good old friend, the distance equation, 10 to the 26.3 minus a -5, which of course is plus 5. So and then you add the other 5, and then divide the whole thing by 5. It becomes 10 to the 7.26, which turns out to be 18.2 megaparsecs. All right, so, or 18.2 times 10 to the sixth